Yeah. So I think, last day I did some, I think, I mean, that was a gross mistake what I said. Okay, let me just repeat that. I was talking, I mean, maybe I was in the flow when I said that, but anyway. So we are talking about a from 0, 1 to the power n to I said 0, 1 to the power
Sir,
d.
sir, screen is not visible.
Oh, I see. I see. Just a minute. Just a minute. Oh, I did not share the screen, it seems. Just a minute. Yeah. Can you see it now?
Yes, sir, it's visible.
Okay. Okay. Yeah. So I was talking about this. Okay. So yeah. So I said it is from 0 to the power n to 0 to the power d, but it should be 0 to the power n. That's the first thing. And
No,
then I said,
that was corrected, sir, in the class. You corrected it in
yeah.
the class only.
Oh, okay. And then
Mhm.
I said something which is grossly wrong. So we said, I said actually, so if we have d qubits, d number of qubits, then I think I said it is called the qubits, but that is not the case. So qubit is qubit is like a d-dimensional quantum state, meaning d-dimensional quantum state, meaning, for example, if you have a qubit, so qubit is like, so it's like something, some vector, unit vector, let's say in c square mathematically. So qubits would be that psi, the states would be in, though this is a normalized vector, so it has a unit norm, and it should mean d. Okay, for example, q trit, okay, q bit is a two-dimensional state, or you can say two-dimensional vector, and then q trit is like a three-dimensional vector, three-dimensional vector. So yeah, vector, you can say quantum state, quantum state. So yeah, it is also unit vector. So here, for example, q trit, so it is in c to the power 3. So there are 3 degrees of freedom. That much, I mean, not exactly degrees of freedom, that will be wrong term, but let's say there are 3 possible orthogonal directions. Okay, a state can be in. Okay. Okay, so yeah, for example, if you consider this atoms and this energy levels, okay, suppose there are 3 energy levels, then possibly you can treat this as a q treat. Okay, this is one mistake I did, and another mistake I think I think not gate. Yeah, so I think I said not gate is a universal gate. That is not the case. So okay, there are two things I wanted to say here. I mean, I think last time, yeah, something I was thinking maybe something. So I said initially, yeah. So this gates like and or not, okay, and let's say copy gate, this forms an this forms a universal set of a universal gate. So this is a set of, not a set of universal, but this is universal. This set forms an universal, a universal gate, I mean set of gates, which is called universal, meaning any, I mean, function, if you consider like this, like this kind of a function, okay, or it could be 0 to the power d, anything. So then that can be factored, or that can be implemented, okay, in terms of this many gates. And then I also said, when a gate is said to be universal gate, so this is as a set, and then as an individual gate. For example, this NAND gate, I think I said, which is a universal gate. So because other operations can be used, I mean, can be implemented using this NAND gate. Okay, I think this is the confusion we had last week. Another thing I think I said, like, I mean, maybe in my mind it was not gate, but I said it and gate. So I was talking about this permutation representation of a gate, and I said and gate, and somebody asked me whether and, because and gate will not be the case. So then I said, okay, you can think about it, something like that I said. But what I actually meant, it is the not gate. So when you can see, like when I said, when I gave you the permutation matrix representation of the not gate, then I said like this is the hint. So meaning I was talking actually about the not gate. Yeah, so that was not the AND gate, that should be the NOT gate. So NOT gate has a permutation representation. So it can be realized as a permutation matrix. Yeah, so these are the things we said. And finally, we talked about, okay, how can we write? So any how can you implement, let's say, using, so this is what I said, I think, last day towards the end, that how to implement any unitary, so any one qubit gate, let's say one qubit, that means any 2 by 2 2 by 2 dimensional, a two-dimensional unitary matrix, how to implement any qubit gate. And we said, okay, using our r, x, r, y, the rotation about x, y, and z, using that, and I think the phase gate, we can construct all possible unitary gates of dimension 2 by 2. That means they are all one qubit gate. Okay, so this is, I think, where we end. And now today I'll talk about two qubit gates. And this is, I mean, yeah, so two qubit gates. So today we'll talk about two qubit gates. And okay, so anyway, two qubit gates. So what I mean by two qubit gate is, like, you have a matrix U, which, okay, so which is from c square times c square to c square tensor c square. So basically it is from c to the power 4 to c to the power 4. So basically u is, you can say that u belongs to c to the power 2 square times 2 square, which is nothing but c to the power 4 times c to the power times 4. So it is a 4 by 4 unitary matrix. Okay, then that can be, so this is a 4 by 4 unitary matrix. Okay, so then this can be treated, this can be called as a two qubit gate. Okay, and we also had seen, like, this c square times c square, this tensor product. Okay, it has a standard basis, and we said, okay, this is, or this can be, or this is generated, a span generated, this can be generated, okay, using the standard, or let's say canonical, sometimes this word also is used. So standard, orthonormal, orthonormal orthonormal uh, unit vectors, let's say, let me denote it like 0 1 0 0 0 1 1 0 and 1 1. Oh, okay, and so this is a set of orthonormal vectors. So it's essentially saying, like, okay, this is, yeah, so this is 0 0 means 0 tensor 0, 0 1 means 0 tensor 1, and 1 0 means 1 tensor 0, and 1 1 means 1 tensor 1. And so this is, essentially, I mean, this equals to this equals to this. So this is ordered, okay, first, second, third, fourth. And then you can say this 0 0, I mean, if you write it in the matrix term, this will be just standard basis elements. Okay, 0 0 0 0 0 1 0 0, and then 0 0 1 0, and then 1 1 1 1. So this is, these are the standard two qubit.
Sir, 0001, last one.
Oh yeah, 0001. Yes, yes, right. 0001. So these are the standard fundamental states, and any state, if you take, so any state psi, yeah, any state psi, so from this yeah, some c square. Okay, so this is any state. So then it can be written as, okay, this can be written as some, yeah, some, let's say, alpha 00 plus alpha 01 plus alpha 1010 plus alpha 1111. So essentially what it means is, see, so you can assume like this, that suppose this is a four dimensional space. So suppose this is c to the power 4, and then we have c to the power 4 here, and then we have a unitary transformation from here to here. Okay, so, and this unitary transformation can be understood, the effect of this unitary transformation on any psi. So u psi can be understood. Okay, what is the output? If this is the input, let's say the psi is input. If I know what is the output of this u corresponding to the the standard or the canonical unit vector, so it is essentially, so this, like, alpha, what is it? Alpha 00 u 0 0, or instead of 0 0 I can just write 0. So this 0 is different from the qubit 0, so this is a 2 qubit 0, plus I can write alpha 0 1, which I can write again, write 0 1 plus alpha 1 0 u 2 plus alpha 1 1 u3. So this 1 2 3 4 are nothing but the first four, like the order, and so here I can also write this as this. That's a 0 1 2 and 3. Also all the here we are writing 0 1, this 0 is not the same as the qubit 0, okay, because it's a 2 qubit state. Yeah, so if we know these things, okay, so 0 1 0 2 u1 u0 u1 u2 and u3, then we know the output of uh, any state psi, okay, when it goes under this unitary operation u. Okay, so now what we'll do is, we had seen, well, first let me tell you three fundamental gates, okay, which will be very useful. I'll spend a lot of time today on these gates, and particularly the CNOT gate. So it is like kind of, so here we have seen, I mean, in classical gates also we have seen that the Fredkin gate or the Toffoli gate, they are all control gate. Okay, so control meaning, in like in the terms of programming, it is like if then else kind of a thing. Okay, if something happens then something happens. Okay, so now since we have two qubits, okay, so we have two qubits, so you can assume like this is a register where we have one qubit here, another qubit here. Okay, and the joint state is psi. So the joint state is psi. I don't know what it is, let's say. So joint state is psi. And then, although I'm writing this as a different register, but it's the same register. So it is passing through this, and then we have u psi. Okay. And now the thing is that there can be two things. One is like, I can develop gates like the classical gates like the C not gate, control not gate. I can talk about, okay, since I have these four fundamental states, the basis vectors. Okay, so I can define this u in terms of the action of this u on those fundamental states, and I can say control means, so if one qubit is a particular type, then this E will act on the other one, so locally. Okay, so I'll define what it is. So let us first say what is a control NOT gate. Okay, controlled as control NOT gate. So meaning, so there are, since there are two qubits, I can assume like one qubit is let's say the target qubit, like where this some unitary operation will act upon, and then the other one, okay, the second qubit, or the other qubit, so the second qubit, or one qubit is for this, and another qubit will act as the control, so that will control the operation on the other one. Okay, so that's the control qubit. Okay, and so CNOT gate is like the way we defined for the classical gate. Okay, classical computation. So it is the same thing, only the difference is like this qubit, the bits will be replaced by qubits. So basically, under this operation, this control NOT gate, let us write it as C NOT gate. So this will turn in this will remain, I mean, this will not do anything on this, and then 0 1 will go to 0 1, so it will not, so it is the same thing, it will not affect much, so it will be identical. And then 1 0, so since the first here, okay, so it is the C naught and 1 1, and let's say 1 1 goes to 1 0, which is C naught. So basically what is happening, when the first qubit is state 1, then the NOT gate is operating on the second qubit. Okay, like here you see, when the first qubit here is at state 0, so this is nothing but 0 times 0, right, as we said. So first state is 0, then it is not acting, the not operation, this not operation is not acting on. Okay, so it's controlling the operation here. And then here also same thing, when it is 0 plus 1, it's not acting anything. And then when it is 1 0, okay, here it is acting, because the first qubit here is the control. Okay, and second qubit here is the target one, and this target operation is like the not operation. Okay, I'll spend a lot of time on this gate a little later, but let me first define the whatever we define in this classical computation, whatever the way we define this control gate, same way I will define it. So just let me write the definitions, and then we'll jump into understanding the behavior of this control not gate and the usefulness of this control not gate. Okay, yeah. So this is the definition of control not gate, and if you talk about Fredkin gate, this Fredkin gate. So this is, we talked about, it is like a controlled swap operation, right? So it is controlled swap gate, control swap gate. So it has the same definition. Only thing like the classical computation, only difference is the bits will be replaced by qubits. So it is like 000. This will go to 000, and then 001 will go to 001. So it will not act anything when the first qubit is 0. Like first qubit is the control here, and 0 1, this will go to 0 1. This will remain fixed, and then 0 1 1, this will go to 1 0 0. Okay, no, it is okay what I'm writing. So yeah, so yeah, just a minute. So here it should be 0 1 1, and then 1 0 0 1 0 0. So then this will change. The first qubit is a control, so it will swap the other two. But here, since the other two are the same qubits, so it will not do anything. And then we have 1 0 1, which will go to 1 1 0, to swapping this second and the third qubit. And then what else? 1 1 0. This will go to 1 0 1, and 1 1 1 will remain fixed because second and third qubits both are 1. So 1 1 1. So this is the definition of Redkin gate. We'll talk about how to implement all this kind of a thing a little later. But okay, let me just define another gate, which is the Toffoli gate. Toffoli gate. Also, let me just write down the input and outputs in terms of standard vectors. So here also you can say, oh, we talked about Toffoli gate as also a control gate. I think it is a control not gate, right? So it is like controlled. So there are two controls here: controlled, okay, and then not. Yeah. So let me just write it down. So 0 0 0 will go to 0 0 0, and then 0 0 1 will go to 0 0 1. So 0 1 0 will go to 0 1 0, and then 0 1 1, which is 0 1 1. 1 0 0 will be just 1 0 0, because there are two controls. So if the first and the second qubits, if they are 1, then only something will happen, something will change here. And then 1 0 1, this will go to 1 0 1, and the change here 1 1 0, this will give you 1 1 1, 1 1 1 will give you 1 1 0. Okay, so these three are fundamental gates in classical computation, because we have seen, I mean, at least the Fredkin gate and the, what is called the other one, this Toffoli gate, that they are universal and they are also reversible. Okay, so they play a big role in classical computation, at least from the analysis point of view, analysis of gates. Okay, now practically that may not be very useful, but at least from the sake of theory, this is nice. Okay, these gates are nice. Now let me focus on C not gate. Okay, let me focus on C not gate. So understanding C not gate. So understanding C not gate. What is it and why it is important? So first of all, you see, I can define this C not gate, that suppose it is acting on some xy, then this is denoted as x. So this is defined at x, or I means plus, you can say this is a modulo sum. Okay, addition modulo 2, and this xy, this belongs to 0 1. So this is one way. Another way to to define C not gate. Okay, and here this is the, let's say, the first qubit. This is the control, and this is the target. Okay, now the interesting thing here about C not gate, that first of all, okay, so first of all, if I want to write the matrix representation of C naught gates, then what happens? What is that? Now see here, in math 2, you probably have done this. Like if you have a linear transformation, so then what is its corresponding matrix representation? That is what is done in math 2. So here the same thing is happening. So I know the transformation, how what it gives you, what is the output of this transformation corresponding to the input, which are the standard basis elements. So from here, I should construct, I should be able to construct the matrix representation of the C naught gate. And let me just define this as, I mean, whatever you did in math too, I mean, okay, so in that course, we did not do it this way because we can use the concept of inner product and do it quickly, okay? But when this was discussed, this topic was discussed in math too, that time inner product was not discussed. So here, let me just write down that C naught, if you want to write the C naught as a matrix, okay? Let's say this is a matrix. So then the ijth entry of this ijth entry will be nothing but I C naught j. So whatever this is, so this will be the ith entry of this. So then you can see that C naught, the matrix representation of this is nothing but a permutation matrix, which is 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0. This will be the matrix representation. You can check it out. So where I and j, they represent the indices of the columns and rows, and they are like from 0 1 2 3. So the 0 corresponds to the first row or the first column, 1 the second row, the second column, 2 is the third row, the third column, 3 is the fourth row, the fourth column. So then you can construct like what is happening. Yes. Now another interesting part about C naught gate is that this gate can be
Sir,
used
sir,
to generate. Yes.
sorry to interrupt. How did you write C naught for a single? J will be a single bit, right? Like C naught on a single number, that I didn't understand. C naught J can't be a single number, right? C naught can't act on single bit, right?
Single.
You wrote I C naught and get J, right?
Yes,
So
yes, yes.
how can C naught act on J? Like,
No, J. So this is what I'm saying. IJ are 0 1 2 3. So here this 0 1 2 3, they are the basis elements of the 2 qubit state. It's 2 qubit space. So
okay, okay.
yeah, so this will span C square. Okay, it tensor C square. So this 0 1 2 3. Yeah, so here I wrote. So yeah, so where is it? Yeah, here. So this 0 1 2 3. So I and j are like this. I could be 0 1 2 3. So they are spanning this c to the power 4. Okay, so this 0 is not the same as the qubit 0. Okay, so this 0 is nothing but basically 0 0 and so on. Okay.
Understood, understood. Sorry,
Yeah,
got
yeah,
confused.
yeah, no problem. And now this C naught gate is very, very helpful because it can generate entangled states. So for example, so the usefulness of this, one usefulness of this, okay, I mean C naught, I mean we'll show a little later that C naught gate, why it is fundamentally important in quantum computing. But let me first say here one usefulness of C naught gate, that C naught gate can be used can be used to generate entangled state. So generate entangled state. So why is that? So let us see that if I give the input like this, so let's say I take any qubit. So this is, let's say, state of a qubit. Okay, so this is any qubit. Okay, state of any qubit, and then suppose the second qubit. So this is the first qubit, state of the first qubit, and the state of the second qubit is 0, and then I apply the C naught gate on this. Okay, so C naught gate on the entire thing. And then this will be what? So this will be C naught, and then this will be alpha 0 0 plus beta 1 0. And so the C naught gate will be nothing but alpha C naught 0 0 plus beta C naught 1 0. Now see my definition of C naught, because it will not act upon this thing 0 0, so it will remain the fixed. Okay, 0 0 plus beta C naught. So first is the control 1, so then the second will change. So this is 1 1. And it is nothing but the Bell state. Probably have done it in quantum mechanics when alpha and beta are equal, like 1 by root 2. Okay, so that's the max. This is the max is something called a maximally entangled state. But for any alpha and beta, this will be an entangled state. Okay, need not be the maximal one. Okay, I'm not talking about that because I don't know how much you have done about entanglement. The thing is, there are two. So let's say, let me. I mean, if you draw this picture, so entanglement is something like if you have two states. Okay, let me do a big picture. So if you have this two particles, let's say, then they have certain states, okay, which I don't know. But I would say that they are entangled, informally speaking. So they have a connection. They are correlated in some sense. I mean, the states are correlated in some sense. That means if I measure something on the second one, the state of this one will change. Okay, even if I didn't do anything with the first qubit. And otherwise, if I do something, some measurement on the first qubit, then this second will change. Okay, the second will change. The state of the second one will also change. And mathematically, this is written as like if I have a psi, let's say this represents the joint state. The psi is the joint state here. Let's say then we'll say like this is entangled if it cannot be written as this. So if it is written as this, some psi 1 psi 2, that means I can have something. Okay, so like this is acting like two individuals. So this can be written as a product state, meaning like psi 1 is the state of the first one, psi 2 is the state of the second one. But if they are not separate, so this is called separable. Okay, this is called separable. Now, if they are not separable, it means I do not know anything about the state of the first one because it also depends on the state of the second one. But how they depend, that I don't know. And here such an example. Here you see this state cannot be written unless alpha. I mean, if alpha and beta are both non-zero, then this can never be written in this particular form. So any such state is always entangled. So this cannot be factored. Mathematically, it can be proved. How can it be proved? Now you can write this as some AB, okay, times some CD. And mathematically, you just apply the definition of the tensor product and then make it equal. And then you'll see, you will reach to a contradiction that A and B, there cannot be any ABCD for which this state can be written. And then if can be written, then you will see that 0 will be equal to 1, something like that you will get. Something like that you will get, which is absurd. I mean, this is just a mathematical calculation. You can do that. So the observation here is mathematically you can prove that this state is not separable, meaning this cannot be factored as a state times another state. Okay, so this is something like whose first state I do not know because it implicitly depends on the second one, and the state of the second qubit also implicitly depends on the first one. So they are somehow correlated. So that's what is called an entanglement. But the question is, the fundamental question here in entanglement studies of entanglement is like how much entangled they are. That means can we quantify? Can we measure the amount of entanglement? Okay, if somehow I can do that, then possibly I can come out and understanding how much entangled they are, how much correlated they are. So does that exist a measure of entanglement? And there exist certain measures, okay, through which you can have a guess. Okay, you can quantify how much entangled they are. I mean, the idea is very, very simple because this probability. So if we measure this one, this state, okay, in the standard basis, like 0, 1, 2, 3 here, the standard basis, because it is a 2 qubit system. So then this alpha square is the probability of getting 0, 0, and beta square is the probability of getting 0. So this is nothing but then alpha square and beta square, let's say, this is nothing but a probability distribution. So it is like a P1 and it is like a P2. And how much uncertain they are, so you can have certain measures for that, like a Shannon interval, something like that. I mean, you can develop new concepts to measure like how much entangled they are. And for example, if I just use the notion of Shannon entropy, then I'll see the Shannon entropy will be the maximum when so beta square can also be written as 1 minus alpha square because mod of beta square plus mod alpha square equal to 1. So P2 is nothing but 1 minus P1, that much you can say. So then you'll see that Shannon entropy, if you take, then so Shannon entropy actually quantifies, let's say in some sense, it quantifies the amount of uncertainty. So this maximum value of Shannon entropy will be obtained when P1 is equal to half and P2 is equal to half. So meaning alpha is equal to 1 by root 2 and beta is equal to 1 by root 2. So in that sense, it is something which is maximal. And that can happen only when you have a Bell state. Okay. So this is one way to look at it. I mean, this is if you consider this as a measure of entanglement, like the Shannon entropy, then it comes like this. Okay, so maybe later on, or I don't know whether I will get time or not. Maybe we will talk about different kinds of measures of entanglement. But here, at least we know that it will generate entanglement when alpha and beta both are non-zero. Whether it is weak or strong or maximal or not, that is an independent matter. But thing is, when alpha and beta both are non-zero, so this will always give you an entangled state. So C naught, if you can realize C naught, okay, if you can prepare the states, okay, some state here which is alpha 0 plus beta 1, and another second qubit is like the state 0, and then if you apply the C naught gate, somehow you can realize the C naught gate, then it will of course give you an entangled state. So this can be used this for the generation of entangled states. So that's why it is also fundamentally important. Okay, now the thing is, why is a C naught gate? Okay, so here I'm always assuming the first qubit is the control and second qubit is the target. Okay, but I can change. Okay, I can put like the second qubit is the control and the first qubit is the target. Okay, I can play a little trick and I can come up with some new gates. Okay, so which I'll call a generalized C0 gate. Okay, so generalized C0 gate. C0 gate. So here, yeah. So when the first qubit, so control, how do I write it? So it is, let's say, the control qubit, and here it is, let's say, the target. Okay, target qubit. Okay. So then, depending on which one is control, which one is target, you can have a C0 gate or not a C0 gate, but a new different gate. Okay. So I'll basically focus on four particular gates, and I'll just give you the mathematical. Okay. So let me just write down the matrices corresponding to those gates, and then I'll talk about which one is the control and which one is the target, and maybe then you can also think about yourself like this could be a like kind of homework. Okay, so let's say my this gate, okay, let me write this gate A. Let me write this as 1 0. So this is what we had, 0 1. This is C naught, 0 0 0 0 0 1 and 0 0 1 0. This was my C naught gate. I can give you another gate which is 0 1 0 0. So all these are permutation matrices, 0 0 0 0 0 1 0 and 0 0 0 1. And then I can again give you one more gate which is like this, 1 0. Can you hear me?
So yes, sir. So
I
sir,
think
we can hear you.
there is a problem with the internet or something like that. Anyway, since it is recording, I'll keep on doing that. I think internet will be back.
Sir, your screen is not visible now. Hello, sir.
Yeah, guys, can you hear me now?
Yes, sir, we can hear. We could hear you earlier also.
Hello. What is happening? Can you hear me?
Yes, sir.
Okay, you can hear us. Okay, you can hear me. Okay. So yeah, what I was doing. Okay. Okay, so let me write one more gate, which is like 1 0 0. So this is another permutation matrix. Let's say 0 0, and this will be fun to see.
Sir, app
If
is not visible.
if you
Like,
apply this gate,
sir,
how it will behave. Okay, so these are called generalized CNOT gates.
sir, pad is not
0 0
visible.
0 1 0 0 1 0.
Sir,
Screen
pad
is
is.
not visible.
Ah, yes.
Just a minute. What I'm doing. Oh, it's Can you see the screen now? I think it is visible. Okay, I can see also in my text.
Yes.
Okay, so 0010 and then another one is this. Let's say 0010 So this A B C D, let's say this four gates. So what is the action of this? You can, so this is my C naught gate. And if you just multiply this matrix B, let's, if you want to understand how does B act upon this fundamental states like 0, 1, 2, 3, then all, let's say 0, 0, 0, 1, 1, 0, 0, and 1, 1, then you'll see that, so B, this will flip means you can say also, yeah, so you can also say flip means it is the not. Okay, so let me say, so not gate is applied, not gate is applied on the second qubit, same thing like A, but here is the difference. So not gate, so target here, see, control I mean for the C not gate in A, what you had is, so when the first one is 1, okay, then only the not gate is applied on the second one. Okay, so first gate is 1, then the not gate is applied on the second one. But I can have a different kind of a rule where if the first state is 0, then let's say the not gate will apply on the second qubit. I can have a different kind of a situation. Okay, so my control here is, let's say in C not gate it is 1, the state 1. Okay, the state of the controller, let's say, is 1, but I can also have a new gate where the state of the controller is not 1 but 0. Okay, so B will do that. You can check it out. I'll just write it down here. So not gate is applied on the second qubit when first qubit has state 0. And okay, this is one more thing. And see this, see, if you check it out, then you will see that if here, so here the control qubit is the second one. Okay, so this not is applied, so you can check it out that not is applied on the first qubit when second qubit is 1. Okay, the state of the second qubit is 1. And similarly D, it will be like not is applied on the first qubit when the second qubit is 0. Okay, that you can say. So not is applied on the
Excuse me,
first
sir.
qubit when the second qubit is 0. So you can have basically these four fundamental control gates. Okay, so one is called the C naught, and others are called controlled generalized C naught gates. Okay, okay. So now let me give you the icons for all these gates. Okay, so the control gate,
Sir, excuse me, sir.
control gate. That is the icon for this is like this. So these are all two qubit gate. If the first one is 1, so when I am in this mm, circle, okay, which a fully filled circle. So and then I'll write it here like there is a circle which is like this. So there is an addition here inside the circle. Why it is addition, or you can say OR. So this is OR. So when this means the icon. So this is for the C naught. So or you can say this is for the gate A. So that means if the first qubit is 1, then the OR operation or NOT gate, you can say, NOT gate is applied on the second one. So that's why there is a plus here. Okay. Similarly, if I want to write the B, the generalized gate, this one, so what does it do? NOT gate is applied on the second qubit when the first one is 0. So I have to use a different icon for this. So let me do like this. Zero means this is the blank one. This is not fully filled out by this color. Okay, black color. So here I will have this. Okay, here I'll have this. So this is the gate B. Okay, the generalized C not gate. Then here when the C for the C gate, I mean for the generalized control not gate C. For this case, so not gate apply on the first. So when the second one is B, so the second one is one. So if this is one, then the first gate is so this not gate is applied here. So plus will be here. Okay, so this is my C, and D is like the same thing. So instead of the filled out, okay, and completely filled with this color, let me say like it is blank, and then we'll have an addition here. So this will be my D. So these are the icons for my generalized not gate. So the thing is, okay, so let me tell you that, okay, so this is a different way of representing, okay, these gates. Okay, so it's not classically, okay, it's a different, something different from the classical gates. But here I would like to mention one thing, like in classical gates, when we had different kinds of icons, and whenever there is a chord like this, a straight line chord, whatever it is, so this represents something related to wire, how the wires are connected, let's say some feeling about the wire. Here, although this represents like this lines here, these horizontal lines, okay, they represent like like wire, but they are not wires actually in quantum computing. There is no wire in quantum computing as such, okay? But the icons, okay, so have wires like the classical gates, okay? So this is a different thing. It's from quantum, from classical, okay? So and note that this is entirely a gate, okay? This entire thing is a gate. So it is not like these two things are not independent of each other. This is entire thing is a gate, okay? This entire thing is a gate. Okay, now so, okay. Now the question is, we talked about one qubit gates. Then the question will be, can I implement these gates? Okay, these control gates. Okay, in terms of, let's say, one qubit gates, and it is also possible. So let me just, I'll not prove it, but you can prove it. Okay, so let me just write down the one gate like this. Okay, one like the gate C. So then the others could be the homework. Okay, so then you can see that this could be written as this. So you have Hadamard gate here, and then here. Okay, but so here what I'm showing you is that this generalized CNOT gates can be implemented using single qubit gates and the CNOT gate. Okay, so although they look like different, but they can be also implemented just by using one qubit gates like Hadamard gate and the CNOT gate. Okay, so this is a generalized CNOT gate. CNOT gate, let's say it is C. Okay, CNOT gate C, and it is implemented. Okay, implemented implemented with Hadamard gate, the use of Hadamard gate and the CNOT gate. Okay, CNOT gate. So this is one to look at this thing. Okay, and there are many. Okay, so I can another control gate. Let me just let it. I mean, let me just put it here. So there is another control gate which is called the control phase gate. Okay, so it is the same thing like the C not gate, but instead of not a gate, it will be one qubit not gate. Let's say here it will be a phase shift. So controlled phase shift, controlled phase shift. So this is okay. We'll write C phase, and there will be parameter delta, which is like 1 0 0 0 0 1 0 0 0 0 and 0 0 0 e to the power I delta. So this is what is called a controlled phase gate. Okay, so basically what happens is So here, control here means this phase gate, phase shift gate. Like phase shift gate was what 100. It is for I delta. This was the 1 qubit gate. So this will be applied on the target qubit only when the control qubit is in the state one. Okay. For example, I mean you can check it out. You can see like what fundamental state which goes to the outputs of the corresponding fundamental gates, fundamental input states. Okay, under this particular operation, under this particular gate. Yeah, and you'll be also surprised to know that the C-phase gate, okay, that can implement it also using. Can you guys hear me?
Yes, sir.
I can't hear anything. Can you guys hear me?
Yes, sir. We can.
Hello.
Yes, sir. You are audible.
I can't hear. Can you hear me?
Yes, sir.
Kaushik, I think sir can't hear us.
Hello.
Yes, sir, I can
What
hear
is
you.
wrong? I don't know. I cannot hear anything actually. Okay, I think I got some messages in my desktop. Oh, okay. I cannot hear you. Okay. So you can hear me. What is this is happening? Okay, region. Okay, let me rejoin then. Okay, I'll be here because okay, just let me rejoin. I cannot hear anything. Okay, just a minute. Oh, guys, can you hear me now?
Yes, sir.
Yeah, now I can hear. Okay, just a minute. There was some problem. Yeah, you have. Did you ask anything? Did you have any doubt?
Sir, can you show how C gate can be implemented from A gate? No, not C. Say B gate from A gate.
Yeah, I mean this can be treated as as exercises. Okay, so
Okay.
I mean, so all the gates, all the gates. I mean, you can do it. Okay,
Okay.
so just all the gates, how you can do it. Yeah. So yeah, and yeah, so this is control phase gate, and control phase gate also can be implemented using the I think the phase gates and I mean phase shift gates, 1 qubit phase shift gate, and this CNOT gate. Okay, so yeah, so I mean maybe I can also leave it as a homework. Okay, let me make a point here. Homework. Where is this? Okay. So this is also homework, like implement C-phase gate using C0 and phase shift gate. Phase shift gate. Yeah, so you can try, and there is one more gate which is a special case of the C-phase gate. So like if you consider if let's say delta is equal to pi, so it has a name because okay, so then it is called C minus. I'll tell you why I am discussing this because minus, because where we have written here, for example, plus here. Okay, so this is plus here. This can be minus also. Okay, so C minus control minus gate. Okay, so which is delta equal to pi if you put, so then this C minus gate will be like 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 minus 1. Okay. Yeah, and then so this will be written as this. So you can see like if this first gate, first qubit is 1, then this will be applied. Okay. Then this, so this minus is nothing but control this shift gate. Okay, where the delta is pi. So so you can also check that. I mean, you can also check. I mean, why I'm saying this? Why I'm saying that this? I mean, this homework. Let's say like C naught and this fetch shift and this thing. Okay, fetch shift and this. Okay, or maybe this generalized gates like the control gates B, C, D. Okay, all this can be implemented using some 1 qubit gate and CNOT gates because they will form universal quantum gates. Okay, so okay, I'll tell you about that, but these all gates, okay, whatever we are talking about. So for n qubit computation, like whenever you have a quantum register which contain n qubits, then any unitary matrix of order 2 to the power n by 2 to the power n can be implemented just by using some 1 qubit gates and CNOT gate. So CNOT gate is enough and 1 qubit gates. Okay, some 1 qubit gates, and not all, maybe some all, some 4 or 5 1 qubit gates. Okay, and the CNOT gate is enough for implementation of any unitary operation or any quantum gate on n qubits. Okay, so that is possible. So these are like some examples I'm giving you. Okay, that this can be done. So here also you can say here also same question. Okay, right. Write this gate, the gate or implement this gate in terms of, or using just in terms of what is called C naught and some 1 qubit gate. Okay, maybe Hadamard gate.
So that is
Hadamard gate.
actually Z gate, right? Like
Yeah,
adding
yeah,
minus
yeah,
one.
yeah, yeah. Phase shift. Yeah, yeah. RZ. So here, because we called it, talked about this, right? So this is RZ. Okay, delta. So this is what is, we called it a phase shift. So yeah. Okay, so now we'll talk about, so the first question here is like what we have seen, that like Toffoli gate, Fredkin gate, they are universal as well as reversible for the case of classical computation. Okay, so we expect that this kind of gates also may be universal for quantum computing. But so because in quantum computing, what happens is everything is reversible. Okay, because everything is a unitary operation. So now the question is the minimal dimension. I mean, minimal number of qubits there was 3. Bits was 3 for Toffoli gate. Okay, you have 3 bits. So the question here is, can I reduce this in quantum computing? Okay, I mean, so can I have universal gates? Okay, or let's say inverse gate on the smallest number of qubits. Okay, that's the question to ask here. But let me tell you that okay, that is possible. In fact, it can also be proved. Almost all 2 qubit gates are universal in quantum computing. I mean, almost all, there is a meaning, but most, you can say most of the gates, okay, are actually universal gates. And I'll give you, I'll prove at least one set of gates which will form a universal, universal. I mean, so that set will be universal gates for quantum computing. Okay, so I'll try to prove that. But yeah, so and other thing is like okay, let me first do that, then I'll talk about the other thing. So I mean, the question what I was trying to tell you is that does there exist, except let's say Toffoli, because you know that classically they are reversible and universal. So quantum mechanically in quantum computing, does there exist gates which are acting on more than 2 qubits and they are also universal? Yeah, there are some gates like that, but there is a different challenge in quantum computing. Okay, so and I'll talk about that also. Like, although we have a very nice thing here, like okay, theoretical speaking, okay, that any number of qubits, n qubits, okay, that can be implemented just by using some single qubit gates and CNOT gates. But this does not also help much, okay? If the number of qubits, if this number of qubits means the n, if it is high, okay? So because what is happening here is, at least here you can see, okay? For example, I had written this here, how many single qubit gates are used? There are 4, okay? 4 qubit single qubit gates like Hadamard gate, okay? 4 times it is used. And there is one CNOT gate. So the question will be, in general, when you have n qubit gate, so you have a unitary matrix of order to the power by 2 to the power n, and if you want to design circuits for that, how many 1 qubit gates are required? And that's where the complexity comes into the picture, a complexity of implementation of quantum gates, okay? Like how many gates, okay, are required, let's say, so how many single qubit gates are required, or maybe CNOT gates or maybe other kind of gates are required, okay, to implement a unitary matrix operation of order 2 to the power n by 2 to the power n. So essentially it means that is a gate for n qubit system, okay? And this is a challenging problem, and this is an open problem in quantum computing, that it is a big deal, okay? I'll tell you why it is a big deal. So let me first show you that single qubit. So this is my claim now. This is my claim now that single qubit, and single qubit gates and CNOT gate, okay, CNOT gate are universal. So the set of, okay, I'll tell you in terms of set also later on. Let me first prove this universal gate. So what I mean by this universal gates for quantum computation, So what I mean by this, okay, let me first give you a roadmap, okay, how it is possible that we can show that this will form universal gates, meaning any unitary operation. So if you have some u, okay, which is, let's say, in c to the power 2 to the power n times 2 to the power n. So this is a unitary matrix of order 2 to the power n by 2 to the power n. Then I want to only use 1 qubit gates and CNOT gate, okay, to implement this u in terms of a circuit, okay? But whenever I say a circuit, it means I need to factorize this u in terms of other lower dimensional matrices, okay? I mean, so if you look at this circuit, for example, here, so it is, so here there is an input, okay? Here the input, here there is output. And then see, when H is applied, this is also applied. So you can say like this can decompose like this entire gate, okay, entire this operation. This is what is it is realized as CNOT gate or whatever, the generalized CNOT gate. So you can write it like this. So you have, let's say, the input psi. Then you can write this H tensor U, this first acted on psi, okay, because individual qubit, this H is acting, okay. Then there is a CNOT gate, which is acting. And then again, there is H times H. So basically, essentially, what it means, this entire matrix is nothing but the C0 matrix, which is here, this, or maybe, yeah, the C, yeah, C. So this matrix will be equal to this, so this one. So essentially, quantum computing, I mean, at least when you're talking about quantum gates or quantum circuits, they're nothing but factorization of a unitary matrix. Okay, and that and then the essential the fundamental problem here is how nicely, okay, how efficiently we can factorize a matrix in terms of some known matrices, which are nothing but the 1 qubit gates and the CNOT gate. Okay, so and this is a challenging thing. I mean, yeah, I'll talk about that, but let us first prove that this will be. I mean, I'll not be able to prove rather this entire thing because this is very huge. Okay, but I'll prove some part of this entire conjecture, and I'll give you a paper which is already available in my webpage. You can if you are interested to know more about this proof, okay, so you can go through that paper, okay, because this is a huge proof, okay, but at least I'll try to convince you that this will be universal, okay. So what I'll do first is the following. This is my roadmap, okay. I will prove this that they are universal, okay. The roadmap. So roadmap. First, what I'll do is, like I said, control not, but not is a single qubit gate. Okay, so control not gate can be generalized into a controlled U gate, meaning controlled U gate, meaning if you have a 2-qubit input, so whether I do not know whether the first one is control, the second one is control, or the first one is target, or the second one is target, but it doesn't matter. One qubit controls the other one, and control here, this controls target on the target one. So let's say the first qubit is the control, and the control could be the state 0 or state 1. Okay, so if let's say the first, like the CNOT gate, if the first qubit has state 1, then on the second qubit, this U will be applied instead of not. Then I'll call a generalized situation here. So I'll call it a controlled U gate. So U not is replaced by any arbitrary 2 by 2 order, 2 by 2 two dimensional unitary matrix, okay, which represents any qubit gate, okay, any 1-qubit gate. So this is a generalized situation here. So controlled U means one of the qubits is controlling another target. So the target, okay, on the target qubit, this operation U will be applied. This is a 2 by 2 matrix. Let's say U is a 2 by 2 matrix. So this belongs to C to the power 2 cross 2. Okay. So during this roadmap, first I'll show that any controlled U operation, any controlled you get, okay, can be implemented using single qubit and CNOT gate. Okay. Second thing, I'll show that any, so I said, for example, Toffoli gate was, I'll talk about Toffoli a little later, but let me say Toffoli gate was like control, no, not the Toffoli. Yeah, I think the Toffoli gate, yeah. So Toffoli gate was controlled, control not. So 2 times there are control. Okay, first 2 qubits are acting like controls. But I can also generalize that. I can say there are k controllers, k control qubits, and the target qubit is the k plus 1. Okay, that also I can say. So I'll first show that the Toffoli gate, the controlled NOT gate, that is Toffoli gate. Okay, Toffoli gate can be implemented using CNOT, okay, controlled U for some U, and Hadamard gate. This I'll show. And then I'll generalize this. I'll say that it need not be control. So control means, let's say I could say C square naught. C square naught means 2 times control. Okay, I'll generalize this and I'll say, try to prove that, I'll give you a sketch of the proof that C to the power k, if there are k control qubits, C to the power k U get. Okay, so k here is bigger than 2, can be implemented using Toffoli and controlled U. And finally, I'll say any unitarium operation, if it is 2 to the power n, sorry, C to the power 2 to the power n to 2 to the power n, okay, so can be implemented using K control you get. So essentially what we are trying to show here, we're first showing that this is, let's say my single qubit. So here I'm just assuming, although, okay, single qubit and C naught. So from this, I'll can generate topology. Okay, topology is a particular case of C to the power K. Okay, C to the power K U. C to the power K means K control, and then I'm applying a U gate on a qubit. So to the power
So
K
excuse me,
gate.
sir. U is U belongs to C2 cross 2, right?
This U belongs to C 2 cross 2 cross 2. This U belongs to 2 to the power K n by 2 to the power.
Oh, okay.
I'll give you examples. Okay, I'll give you example. I mean, if this U is not at K is 1, then it is like control NOT gate. But I'm saying NOT gate is a 1 qubit gate. So instead of taking NOT gate, I can consider any general qubit gate, any unitary operation, any 2 by 2 unitary gate. Okay. Got it?
Yeah, yes, sir, yes.
Yeah. And from here, then I'm saying that I can again consider any, I'll say that any 2 to e to the power n, okay, can be implemented using C to the power K U. So that means everything, this entire U can be implemented using just single gates and C naught gates. This is my goal. Is that clear? Because this is very, very fundamental. So, and we need to understand this. Okay. Is that okay?
Sir, C power K means K controls, is it?
Yes, 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 yes. Where did I write it? So, oh, I didn't write it here. Okay. Okay, let me
There
write.
you second step you wrote.
Oh, okay. No, I did not write the definition. Okay, let me just write. So C to the power K you get means K control qubits. But which one is controlling? Which one I am not specifying that. Okay, I'm just saying K control. There are K control qubits. I'll give you examples. Don't worry. K control qubits, and they are controlling one target qubit. So even if you have n qubits, some may be idle. Okay, let's say K is equal to 2. So you can have a situation. Let's say you have. Okay, I'll give you. I will implement this thing like the TOEFL again, and then I'll explain. Okay, but I'm running out of time. Okay, so first of all, let me talk about controlled U gate. How to so because that's my first step. First step is I want to implement. I said control U gate can be implemented using single qubit and CNOT gates. Okay, so what is my controlled U gate? So there is one qubit which is acting as a control, another one is a target, and control U means on the target one, I'm applying the U gate. Okay, U here is a 2 by 2 unitary matrix. But as I said last towards the end, I said that there is a parametric form of all possible unitary matrices of order 2 by 2. Okay, and I am writing just the parameterization here, because I need to implement this U, right, in terms of single qubit and CNOT gates. So that's why I have to write this expression. So e to the power I delta minus alpha by 2 minus beta by 2 cos theta by 2 minus e to the power minus I delta minus alpha, by 2 plus beta by 2 sine theta by 2. Here it is e to the power I delta plus alpha by 2 minus beta by 2 sine theta by 2 and e to the power I delta plus alpha by 2 plus beta by 2 beta by 2 cos theta by 2. And here this there are 4 parameters delta, alpha, beta, okay, theta are all real numbers. And now my conclusion is this is just again a homework. Okay, I'll not prove it because I don't have time to prove it. I mean, nothing proof is nothing but multiplying. Okay, so I am saying that you can always be written as this. E to the power I delta, or maybe you can, okay, let me just write it down. R Z alpha, because see, remember in last class, we talk about that any matrix, unitary matrix can be implemented using XRZ or XRY, okay? And the phase control phrase, so, or the phase shift, okay? So RZ alpha, RY theta times RZ beta. I mean, you just pick these matrices, multiply this, and
Sir, if
okay,
you are writing,
instead of,
it's not visible, sir. R is it R? Like it stopped at delta only, sir. If you are writing,
yeah, I'm writing.
it stopped at some after U gate matrix. Just delta is written. It stopped. Screen 4 rows.
Oh, okay, just a minute, just a minute. Yes. Can you see my screen now?
Yes, sir. Now things are visible. Like they
Okay,
are.
okay, okay, okay. Okay, I can also see it in my desktop. I checked it. Okay. Yeah, I was writing something. Yeah, so what I'm saying here is any unitary matrix has this kind of a parameterization. Any, all 2 by 2 unitary matrices. Okay. So can you parameterize using these 4 parameters and this of this particular form? And this U can be written as this, or U to the power I alpha, I tilde. Also, you can write it as like some identity times EI delta. So you can write it like this. Okay, or let me give you a notation. So this is, let's say, some phi delta. Okay, and then remaining the same thing. Ry, let's say theta, Rz, let's say beta, where this phi delta is nothing but e to the power I delta 0, 0, e to the power I delta. Okay,
Uh,
so everything in terms of matrix now.
Sir, last time you gave RX matrix, I think, at one place for alpha.
No, that is okay. So yeah, what is that?
Last time you gave one RX, one RY, one RZ, and phase matrix, but
Yeah,
now
yeah,
you
yeah.
give two RZ and RY. Is it like possible or equivalent? Are they equivalent or
Yes, 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 it's equivalent, equivalent. I mean,
also?
so I said there are some IA, B, C, D, right? So you can change the ordering. I mean, that also can be written, this also can be written this way. But
No,
here I need to give you an implementation of in terms of gates. So I need this kind of an ordering. Because if I do this kind, you can multiply and see, okay? There I did not tell you what was my ABCD. For some ABCD, there will be something, right? I did not give you this representation of U, but here I fix my representation U. But you can change, let's say, the first column into second column into first column. So that will also be a unitary matrix. But first column can be obtained for some special value of alpha, beta, gamma, alpha, beta, theta, delta, and so this is one parametric form. But you can change, for example, you change this to this and this to them. Then still also that is also the same thing, right? But then here we
not
have to make
regarding
some
orders.
adjustment.
Sir, sorry, not regarding orders, sir. Regarding
Yeah,
the matrices only, U is composed of currently four matrices, right?
yeah.
So
Four
in
means one
them,
is scalar, one is scalar, one is
one is
scalar.
phase shift, okay.
Yeah,
But
yeah.
in that last time you give one is RX, other is RY, other is RZ. But here you give both are RZ only.
Oh
So
no, no. Oh, sorry, sorry. Oh, that you were saying.
exactly. One of them should be
Uh,
RX, right? For alpha, I think it.
uh,
So
Yeah, one of them
I,
first
that
was
should
RX.
also work, and this should also work, right?
let me check. I think what was that? I don't remember. Okay, let me just say here what I
RX,
said.
RY.
I mean, anyway, that doesn't matter. We can do that using RX, both RX. I mean, we just have to multiply these vectors and just sorry matrices and just check whether it is working or not. Here, I think I said in terms of RX, RY, RZ, right?
Yes,
Where
sir.
is that?
RX,
Yeah,
RZ.
yeah, here.
There, sir. RZ, RY, RX.
Oh no, both are Z here.
Oh, okay. Sorry, sir.
Okay, no problem. Anyway, no problem.
Sir,
But you can check it out, right? You can multiply and see like what is happening. Okay, whether it is coming this to be true or not. Okay, that you can check. But anyway, so the thing is, if you assume that this is the, I mean, you assume meaning this is the problem of all unitary matrices. When I say all, it means what I'm trying to tell you is that for some specific value of alpha, beta, delta, theta, you will get a unitary matrix. So you just construct a unitary matrix. So there will be you will be able to find some values of these parameters for which it will give you that unitary matrix. Okay. Otherwise, you can just check it out, just multiply, because you know formulas of this one. Okay, maybe I can put it as a homework. If you don't get it, just let me know. Because I don't want to prove these things. Okay, it will be very long proof, and this is nothing on matrix multiplication, nothing else. And these are very standard actually. Okay. I mean, okay, these are very standard. I mean, there is nothing. I mean, when first time it was discovered, it was challenging thing, but once you know the formula, it has nothing, right? So okay, yeah. Now what I'm saying here is, and now this is interesting. Okay, so any we use this. Okay, now I will write this u. Okay, this is another representation I'm giving. So oh, another, because I need to form this what is called the circuit. So another representation I'm giving. U also can be written as this. U also can be written as phi delta A sigma x B sigma x and C, where is another way of writing the same thing, where A will be equal to Rz alpha Ry theta by 2, B is Ry minus theta by 2, Rz minus alpha plus beta by 2, and C is equal to Rz beta minus alpha by 2. This also you can check. Okay, this also you can check. And there is sigma x now here. Okay. And this ABC, okay, if you just multiply ABC, then one property of ABC, A times B times C is equal to identity. This is very, very important. Okay. And this formulation actually I'll use to implement my circuit for this U using 1-qubit gates. Okay. So let me first 1-qubit gate and the control gate. So let me first write it down. Okay. What is the I mean, how do I implement control U operation or control U gate in terms of this ABC? Because of this factorization, now what I can write here is the following. So my control U gate is like this. It's like this. Okay. So I'm applying U on this when my first qubit is 1. So first qubit is 1. So first the state of the first qubit is 1. Then on the second qubit, U will be applied. I'm saying this is equal to this. I mean, this can be implemented like this way. And I'll tell you why. This, then first C here, and then there is a control here, and then there is B, and then there is one more control, and then there is A, and there is one gate here, which is delta. So delta is a phase. This delta means it is just the phase shift delta, which is a phase shift gate, 1-qubit gate, which is acting on the first qubit when it is first qubit is 1. Okay, this is what it means. Delta. Delta means is a single qubit gate. Here when I'm writing delta here, it means when the first qubit is 1, then this delta gate is operated. Okay, or applied. Now, why does this circuit will represent this? Okay. Now there are two things to observe here. Okay. A times B times C equal to identity. Okay. So now see, if the first, see what I have to do when I have some unitary matrix, it is enough to know that when this matrix acts on the fundamental 4 2-qubit states, okay, and then the outputs are the desired outputs, then we are done. We need not to check all possible states psi. We'll only check for the 4 fundamental states. Now see, if the first target is 0 here in the left hand side,
if this is 0, then this U will not be applied. That means whatever qubit it is, this will remain invariant. So the output, so if it is psi is 1 or 0, okay, it could be 1 or 0, right? Psi. So if psi is 1, then this U will not act on 1 because the first qubit is 0. We have to check whether this is also true here or not. Now see here, if the first qubit is 0, then this will not act, this will not act, this will not act. So on the second qubit, whatever it is, let's say it is psi, so it could be either 0 or 1. Then since this NOT gate is not acting and this second NOT gate is also not acting, so it is nothing but C times B times A, right? So A times B times C, because first C will act, then B will act, then A will act. So, but A times B times C is nothing but identity. So it remains invariant. That's the first thing to observe. So I am getting the same output for the same input here. So, like the circuit in the left hand side is equivalent to right hand side circuit when my input first qubit state is 0. You understand this? Because A times B times C is equal to identity, right? So when you write C, so first psi will act on C, then B will be acted on, then A will be acted on. But A times B times C is equal to identity. So psi remains the same. So we are done when the first qubit is 0. Now we have to check when the first qubit is 1, whether U is acting on the second qubit or not. So let me just delete this part and then say like what is happening when the first qubit is 1. Okay, first qubit is 1. So yeah. So when the first qubit is 1, then I see that this on the second qubit U is acted on. Okay, U times psi. But I know that U is exactly equal to this. Okay, so U is acting means see here, see the circuit here. See the circuit here. So when this is 1, the first qubit is 1, and second qubit psi, then C acted on psi. Then there is a C naught gate. Okay, you can say this times. Okay, if you want to the write entire thing, okay, so then I have to write it a little different way because there is a C naught gate. So let me write it this way. So my original input was 1 times psi, right? This is my input. Then first C gets operated. See, when C gets operated on the second one, that means first one I'm not doing anything. So I'm writing the matrix C here. Then my C naught gate is operated on. Then my B is operated on. And then again C naught gate, again A gate. But C naught gate is nothing but I times sigma x. Again, whenever this C naught gate is there, it is nothing but I times sigma x because sigma x is the NOT gate. So now I can realize this by writing just sigma x and forgetting about all C naught and other things. I can just say first psi was there, then C was there, then sigma x applied, then B applied, then sigma x applied, then A applied. And what is that? Is that U times how? No. Why? Because psi, there was a phi here. So this part is done. Okay. So but this part is equal to what? See, this part is done here. Here, this part is done. But this part is not exactly U, but phi inverse delta times U because phi is unitary. Okay, you can say phi star delta. Phi delta is nothing but the diagonal matrix, this one. This is invertible because this is unitary. So then this is then what is my output here? So this is nothing but you can say phi delta inverse, okay, U psi. And then you can also write this equal to e to the power minus I delta, e to the power I delta, and so on. Okay, U psi. Or you can just say e to the power minus I delta times U times psi. But now here you see that on the first gate, I am applying delta. So when I'm applying delta on the first qubit, My second qubit, I'm not applying anything, but the second qubit is what? Second qubit, then I'm applying identity, just like I discussed before. So when delta is applied on the first one, okay, whatever it was, let's say it is 1. So delta gate, actually it is RG delta. Then the second qubit, there is only actually identity. So if I want to write it, I mean, you can tell me if you don't understand it, okay? So I'm actually applying RZ delta times identity to what? To this 1, because the first qubit was 1. First qubit was 1, so I'm applying it on 1. See, there is no gate applied here up to this much on the first qubit 1. Only delta acted here, okay? So when this applied, this RGA applied on 1, then on the second qubit, I only applied I, but on the second qubit, my entry is this, e to the power minus I delta U psi, okay? U psi. Now, if you just, so this is nothing but RZ delta times 1 times this, okay, e to the power minus I delta U psi. And then you'll see here, if you multiply, okay, or there are two ways to prove it, but anyway, so you will get out this I delta, and then scalar, this also will come out, and then you will have just U times U psi. So and this will be the minus I delta, which is nothing but 1. So ultimately you get the output will be this U times psi. So when this is remain invariant, and this is my actually what I wanted to do, when the first qubit is 1, U is applied on the second qubit. You understand this? I can explain it again. I mean, only thing is to understand here is the last part. Last part is very easy because e to the power I delta I'm applying on the first one, like RZ gate, okay? And then on similarly on simultaneously on the second qubit I'm applying, not doing anything. That means I'm writing I'm applying identity. This was the input. This was the input when my state is here. My state is here. Then this is the input. This is the input, and this is the gate. So if I apply that, I get ultimately first qubit as 1 and second qubit as U times psi. This is what I wanted to get. And so it proves that the circuit in the right hand side is equivalent to the circuit in the left hand side. So that means controlled U operation, okay, or controlled U gate can be realized, can be implemented using C naught gate, okay, and a CBA, which are actually single qubit gates. CBA, they're nothing but this is A, this is B, this is C. Okay, these are nothing but single qubit gates. So controlled U, okay, can be obtained using this single qubit gate. Okay. Yeah, so I think time is up, but I wanted to finish this. Okay, let me do one more thing, and then maybe I'll finish this because this is the main thing. And next day I'll just say something, and then we'll. So next, what is my next roadmap? In the roadmap, what was my next thing? Next thing is if it is C to the power k, or in special case if it is C to the power 2.
So one second, one small note. In the second qubit, where is e power iota delta coming from? Is delta a function of alpha, beta, gamma?
The here.
And beta.
Here.
Yes, there was no delta, right?
No, there was delta
A
because
sigma
this
x, B sigma x, C.
That is equal to, here you see, this is that part.
Yes, and there is no delta over here, right?
Yeah, here is delta.
Oh, okay, from that relation. Okay.
So that inverse will come here, okay, on the left hand side. So this is this one. So this is U inverse, right? Phi inverse delta times U.
Yes.
Okay, yeah. Okay, so my second goal was to write this, to implement this K control gate, okay? K control gate using TOEFL and control U. But first, before that, I need to implement TOEFL. Okay, so this is my final goal in the second part. But before that, I need to see whether TOEFL gate can be implemented using CNOT gate or not. or control D gate or 1 qubit gates or not. Okay. And now I'm trying to prove that my Stoffeli gate can be implemented using C naught, control D, and Hadamard. See, control D I already have seen. This can be implemented using C naught and 1 qubit. So if I prove that Toffoli gate can be implemented using C naught, control D, and Hadamard, then I can conclude that C to the power k, okay, C to the power k not gate, let's say our U gate, can be implemented using single qubit and C naught gate, because Hadamard is single qubit, C naught is the C naught, and control D is also collection of or combinations of one single qubit and C naught. So just let me just write it down, okay. So for Toffoli gate, so this is the implementation of Toffoli. Of Toffoli. So here, what is the Toffoli gate? There are two controls. Okay, so what should be the icon? The input is 3 qubit, right? So the icon would be like there are 3 qubits. Okay, if the first qubit is 1, second qubit is 1, then I'll apply the NOT gate on the third one. So the plus sign. Okay, I'll apply the third. So this is what is my Toffoli gate. Okay, now I want to write this entire circuit. Okay, this is circuit means this is just a representation of the Toffoli gate, the philosophical representation. But I have to implement this, right? So I have to implement. How do I implement this? So I want to implement this using just 1 qubit gate, C naught gate, or maybe control D or something like that. So now I'll just give you a circuit, and then you can again prove that the same thing is true. Like the way I explained it, so similarly it can be also explained. So this is my circuit. There are 3 qubits. Okay, and now first I will apply Hadamard on the third one. Then I apply a control V gate on the second one. By the way, I know that's why, I mean, it is available in books. That's why I'm just writing it down, circuits. But if you do not know, this could be a very, very hard task, because it is nothing but a matrix factorization problem, which is in general very hard problem. Okay, so writing a unitary matrix as a product of unitary matrices of lower dimension, okay, product here maintains a product, so could be a difficult job. Okay, so this is control V. I'll tell you what V is, and then I'll again put a control here, and then here I'll write again one control, which is, I'll say V dagger, which is transpose of V or conjugate transpose of V, and then one more control here, and then again I have this one more control. Yeah, that is what I was talking about here. And then I have Hadamard here. Oh, sorry. So I have here one more Hadamard, and then this. Now see, this is an interesting part. This is a 3 qubit situation, but this control, okay, let me use another color. This control is between the first qubit and the third qubit. And this is challenging. I mean, if you want to study the complexity of quantum circuits, so this is the fundamental problem, that this is called the height of a control gate. This is a control gate, control U gate. Here U is V, by the way. So control V gate, okay? But the first one controls the third one. So need not be, it is, I mean, it is need not be true that only consecutive qubits, I mean, one could be the target and the control, okay? But the first can be controlling maybe the last one, or maybe fifth one controls the 10th one, and so on. So this is called a depth or the height, okay, of a CNOT gate. Actually, there are many things. If you go into the advanced study of designing quantum circuits, you will see that these things we want to avoid. Meaning, when you have a physically, let's say, suppose one day it's possible to design a chip which contains this kind of circuits and this that. So that means physically this qubit is far away from this qubit, okay? And you want to apply a CNOT gate using those two qubits. So which is implementation could be really, really experimental. It could be hard, but this is how it is, okay, for the time being. So yeah. So now suppose, okay, what is V here? Any idea what V could be? No. So V, okay, V here is 100I. So this is just a control phase gate. I mean shift, fetch shift gate. So V is unitary, and of course V star, V dagger is also unitary. Then you just check that. So what is this gate? Toffoli gate. You know the Toffoli. You can create the Toffoli matrix because I gave you the recipe how to do that. Then what is this? So first we apply H. So let's say your input is something like psi1 times psi2 times psi3. So this is how the circuits should be realized. Let's say, okay, I'm telling you this. So first what you are doing is you are acting H on the last one. So that means your identity is applied on the first two. Now once you do that, you are applying the control V, okay, on the first two. So that means identity times here CV, control V gate, okay. And then you are applying some C naught gate on the first two. So this is C naught times identity, okay. And then after here, so then again identity times control V, then again C naught, okay, C naught times identity. And then again, and this is the very big thing. So this is, there is a like, the second qubit, nothing is acted on. The first qubit and the third, last qubit, there is an action. So it is very difficult to write it. But let me say I and this two like this C, and I'll write V here. Okay. So, and this is, it is not C times V, but it is CV. Okay. Because control V. And then again, on the last one, you are acting this. So it is like this. So that means this entire Toffoli matrix, if you write, it can be decomposed as product of this times this times this times this times this times this times this. And then you'll get the corresponding output, whatever the output is. Okay. So this is also a vector factorization. Now this I'll give you that as a homework, or even if you do not consider it as homework, question will be how to check without, let's say, without any calculation, how to check that this will actually represent the Toffoli gate. Okay, I will possibly give you a hint that this part and this part are just the reverse. Okay, so this is HV and this not, and here also not H and the control V, but control here is between the second and the third one. Okay, this is the difference. And then it is just the H here. So what is happening? You want to have this. If that is both are one, so this is one, then this is psi. So you want to check for other qubits here, whatever you do here, if they are zero or one of them is at least zero, then you have to check that nothing is affected. Okay, then how do you realize? Do you realize this from the circuit or not? That if one of them is zero, this is, let's say, zero, this is one, or this is one, this is zero. At least one of them is zero, then nothing should be acted on the third one. Okay, this is what you have to make sure. And next thing is that when both are one and this is psi, then the psi should be changed to, I mean, not get should be applied to psi. Okay, that you have to make sure. And here this V is this one, 100I. Okay, so you try to explain it in your way, or mathematically you can also check writing all down all the matrices, what is happening, whether this is giving you the filling or not, the Stoffeli gate or not, it represents Stoffeli or not. But I gave you a hint how to do it, because you can see that left hand, right hand, there is a symmetry. Okay, around this point, there is a symmetry here, this and this, not exactly symmetry, but it's kind of a symmetry. Okay. Yeah, I think I'll stop here. Okay. And maybe next day I will talk about the third part, that how this unitary u to the power n can be implemented. But this is a challenging thing to do. So what you can do is, so if you go to my home page, okay, my personal home page, if you go, if you just click, I write my name, maybe I'll show it to you. So let me, what is that? Google, right? So Uh, yeah, so Okay, so if you write my name, yeah, so this the first link will be my web page. And if you go to teaching, and then you go to previous years like the spring 2019 2020, if you click here on quantum computing, this page will open. Okay, and then here in resources, the first link, elementary gates for quantum computing. Okay, so this is archive version, and in bracket there is a journal version, but you will not have subscription because you're outside the campus. So you read this one. This is what is called elementary gates for quantum computation, and this is the paper which is appeared in 1995. So and this is the paper where they'll discuss, okay, how u to the power n means in unitary matrix of order 2 to the power n by 2 to the power n can be decomposed, can be written as a product of some rotations, okay, that I'll be using, for the implementation of for proving that that the C naught gate and the 1 qubit gates, okay, they give you they are universal gates, let's say. So this decomposition will be used there. So I'll not, because this is I mean, this is, let's say, a big paper, I mean very large paper, so I'll not discuss everything about it. But if you want to see, then the proof is here. Okay, you can just read it, that much I can say. But I'll briefly discuss. Okay, so what I was doing here, everything is here. You see this ABC equal to identity, this lemma 4.3, you can see. Okay, there exists ABC and this all these things. So you can read it if you are interested, or maybe you will be happy to, yeah. So this matrix is nothing but this EZ, I mean RZ, like identity, I mean RZ times identity. So yeah, so yeah, and otherwise if you are not interested, then yeah, I'll discuss little bit about this, and then yeah, so that will be like, there will end about discussion on quantum gates, and then we'll turn into talking about so we'll move to talking about quantum algorithms. Okay. Otherwise, you can just have a look at this to get a feeling. And by the way, this is an open problem. Okay. I mean, this I'll discuss next day, but let's to give you a hint. Still, it is an open problem. Like, because you see, okay, I'll show you maybe if you see the paper here. Just a minute. So number of gates. Okay, so question is, if you want to implement u to the power unitary matrix of order 2 to the power n by 2 to the power n, how many elementary gates are required? Elementary means 1 qubit and C naught. Okay, and that is exponential. So it is not of any help. So so it will be n squared times 4 to the power n number of. So here it is. Yeah, here it will be approximately, yeah, order of 4 to the power n. But again, this 4 to the power n is nothing but here it will be a controlled c to the power k, c to the power k times control u. Okay, and that again can be implemented using order of n square. So it will be n squared times 4 to the power n. So here, whatever they are saying, theta of nq 4 to the power n. This is a problem. Okay, so then that means exponential number of gates you have to use, elementary gates, in order to realize it to the power n by you, like a unitary matrix of order 2 to the power n by 2 to the power n. Then the question will be, which unitary matrices can be implemented using only polynomial number of gates, which is an open problem. Okay, can we classify, because this is exponential, can we classify all unitary gates, okay, which are on n qubits, let's say, which can be implemented, okay, efficiently using polynomial number of gates, polynomial in terms of the input, like polynomial in terms of n number of qubits. Yeah, that is still open problem. So yeah, so although yeah, quantum gates are good, but when the number of qubits increase, okay, so if the number of qubits increases, so then number of gates also exponentially increase. Okay, so for huge number gates, okay, huge number of qubits, it is a difficult problem in quantum computing. Like at least in circuit model of computation, it is difficult to achieve that thing. Okay, so we may have to use some different kind of a model, not in terms of a circuit model or computational model, but we have to probably use a different kind of idea. Okay, but at the same time, the question will be like, can we classify those unitary matrices which can be implemented using polynomial number of gates? So, and that is an open problem. Yeah, so I'll stop here. If you have any question, you can ask me.